I was watching the other one, and it missed some of the beginning.
Yeah, it missed the part on radicals, which, as you'll see when we work through it, really that section isn't. We're going to be doing that as we go, and hopefully it'll make sense. Okay, so K, we need to find K, and to get K, what we do is we take that answer 3 and we plug it into the function. So that means we're going to go up to our function and we're going to replace all the x's with 3. So this should be, let's see, 3 squared. We're going to square the 3 minus 6 times 3 and then plus 13. So square 3, we get 9 minus 18 plus 13, and that should give us negative 9 plus 13. We should just get 4 here. So that means that the vertex as a point is the point 3, 4. And that will represent the lowest point on the graph because our parabola opens up, we know it's going to be at the bottom. So step 3 is to do a quick sketch. And what we're trying to do here is use the vertex to determine whether or not we have x-intercepts or not. So if I go and plot the vertex, 1, 2, 3, 1, 2, 3, 4, we don't really need to be real precise with that. There's my vertex, but my parabola opens up. So I know my parabola comes up like this and like this. And notice that we will have no x-intercepts. No x-intercepts because the parabola does not hit the x-axis. So that means that when we get to step 4, which is x-intercepts, we're going to skip this step. All right, we're going to save ourselves some time and not go try and find them. Now, if you did that step, you would actually have to do this. But again, you'd be wasting time. You'd be doing this, and if you do that, you're going to use a quadratic formula. And when you use a quadratic formula, you're going to wind up getting a negative number underneath the square root. And then that's going to introduce imaginary numbers. And we already said that we don't want to get too deep in the imaginary numbers. We just know that we don't have a real number answer. So that whole quick sketch idea is just to save you time. That's all it is, just to save you the effort of having to do step 4 when you don't need to, in this case. All right, so I'm going to go to step 5 then, which is the y-intercept. And to find the y-intercept, all we do is plug 0 into the function. So when we plug 0 into the function, we get 0 squared minus 6 times 0 plus 13. That just gives us 13. So we have a y-intercept of 13. And that's it. We're supposed to graph this now. Now, unfortunately, this graph does not give us enough room to do this. Okay. So let's put our information on the graph. We have a vertex of 3, 4. So we go out to the right 3 and up 4. There's our vertex. We have a y-intercept of 13, so we actually have to kind of add to this. 11, 12, 13. There's our y-intercept. And we know that this thing opens up. And we also have this thing called the axis of symmetry, which means that our parabola should look like a reflection over that blue line. So this is where you're just going to do the best you can to draw it. And just make sure that you draw a little U down here. Don't make it a V. And just come up and try and connect through that point. And then just do your best to make the right side look pretty close to the same thing. What you don't want is something like this. You don't want like that, okay? Because then it doesn't look symmetric. So you're just trying to get that symmetry to look somewhat decent. Understand? Any questions on that?
So the reason why you put 0 in step 5 is because there's no x-intercept? Is that why?
The reason I put 0 where?
In step 5?
No, you always put 0 in to find the y-intercept. Because what we're asking ourselves is where does the graph hit the y-axis, right? That's the question. Where does it hit the y-axis? Well, any point that hits the y-axis, okay, any point that's on the y-axis, no matter where it is, if you look at that point, the x-coordinate is 0. All of these. And so that's why to find the y-intercept, you're always going to replace x with 0. So it's more that you plug 0 in every single time you want to find the y-intercept. It has nothing to do with the fact that we skipped step 4. Step 4 is completely a different idea. Does that make sense?
Yeah.
Okay. Okay, let's move on and do another one. Okay. Let's do this one. This one's got a little more stuff we have to keep track of. So I'll first identify A, B, and C. So I have -1, -2, and -1. Just make sure you get those signs correct. And now step 1, which way does this parabola open? Up or down?
Down, negative.
Down,
Right?
okay, down, and that's because A is -1 and that's less than 0, right? Negative number means we open down. Step 2 is to find the vertex. So we will use the formula H is equal to -b over 2 times A. For us, -b would be +2, and then 2 times A would be -1.
So that'd be -2.
So -2 where? Oh, yeah, on the bottom,
On the
yes.
bottom.
So 2 over -2 is -1. And give me a second, I've got to calibrate my pen. See if this works. Where is it? Where is it? There it is. Okay, so now that we have H, we go find K. And to get K, all we're going to do is plug -1, what we got for H, into the function. Now be extremely careful here because we already have a negative out front. Does everyone see that negative out in front of the x squared? So that negative is like a -1. So we actually have this. We have -1, and then we have to do -1 squared because we're supposed to square x, but we're replacing x with -1. So then -2 times -1 again, and then -1. So you see how it's all these little signs you have to be careful with here? Like that negative right there, right? Just be careful with it. Now let's do order of operations. We'll do the exponent here first. What's -1 squared?
1.
1, but then we have a -1 in front of it, right? So it's going to be -1 times 1. And then what happens when I put this together here? -2 times -1, because that's multiplication.
Would that be
It'd be
positive?
+2, 2, right? Positive, so +2, and then we still have -1 out there. The -1 times 1 is -1, +2 -1. Isn't that just 0? That's just 0. So our vertex is the point -1, 0. So now we do a quick sketch to figure out how many x-intercepts we have. So we go -1, 0. It's going to be, let's see, -1, and then 0 means you don't move up or down at all. So I'm just going to put a point here. And which way does it open?
Down.
Down. Okay, so it opens down. And so how many x-intercepts do we have?
1.
We just have one, okay? One x-intercept. So do we actually need to go through and do step 4 here? Do we need it? Or do you already know what the x-intercept is?
Wouldn't it just be -1?
Yeah, I mean, we have it, right? This point right here is actually that point. We know the x-intercept. It's -1, 0. So there's no work to be done. That's good. We haven't had to use a quadratic formula yet. I move to step 5. I find the y-intercept. And that I do just by plugging 0 into the function. So I'm going to just plug 0 into the function. And when I do that, all I should get is -1 because everything with an x in it goes away. All right, and from that, I should be ready to graph. So if I plot my x-intercept at -1, 0, it's right there. And if I plot my y-intercept at -1, that's right here. And then think about drawing a parabola that opens down with an axis of symmetry of that blue line. Kind of zoomed in on this a little bit. So now it's going to go like this and like that. That's all I need. All right, let's look at the next one. So next one, let's see. Can you tell what A, B, and C are here? Be careful. So what's A?
2.
2, okay. What's B?
8.
8. And then what's C?
0.
Whoa. Man. The program is freezing up on me. This has been happening more frequently than I like. So A is going to be 2, B is going to be 8, and C is going to be 0 because there is no number by itself if this ever restarts. Come on, several minutes? We don't have several minutes. Okay, try it again. Okay, A was 2, B was 8, C was 0. All right, so it opens up because A is a positive number. The vertex, we find H first by doing -B over 2A, which for us is -8 over 2 times 2. That's -8 over 4, that's -2. Then we find K. Take that answer, -2, and plug it into the function. So we're going to have 2 times -2 squared plus 8 times -2. Again, I'll point out, you just have to be real careful here because you're wanting to square the x, right? And we're plugging in -2, so you have to square that first, and then after that, you'll hit it with the 2. Order of operations, exponents comes before that multiplication. So what I'm saying is don't multiply the 2 times the -2 first. Do the -2 squared first. So we'll get 2 times, now -2 times -2 is 4. And then this should be -16. So So we get 8 minus 16, which is negative 8. So we have a vertex of negative 2, negative 8. Any questions there? Quick sketch. Okay, negative 2 for my vertex, negative 2 to the left, and then down 8. Who cares where that is? It's somewhere down here. And my parabola opens up. And what does that mean? How many x-intercepts am I going to have?
2.
2.
2, right? And that means I have to go find them. All right. So now I actually have to do step 4. So for step 4, finding the x-intercepts, what we always do when we have x-intercepts to find, what we always do is we take the original function, in this case 2x squared plus 8x, and we set it equal to 0. Now, once we get here, we have a quadratic equation, and you have options, right? There were 3 options. There was factoring, there was that short method, the square root method, right? But that we could only use if we were missing the x term. Are we missing the x term here?
No.
No, we have an 8x, so we can't do that square root method. But then we also have the quadratic formula. So I know a lot of students, they fall in love with the quadratic formula. But this one actually factors really, really nice because we only have 2 terms. If you were asked to factor the left-hand side, you could do a GCF of 2x. You could pull out a greatest common factor. They both have a 2, they both have an x. And when you do that, you'd be left with x plus 4. So hopefully you agree with that. If you distribute the 2x back through, you should get 2x squared plus 8x. And now that we have factored it, we can set each of these equal to 0. So this method right here of doing the factoring is much faster than the quadratic formula would have been. Let's do the equation on the left. If I want to get x by itself, I need to divide both sides by 2. But 0 divided by 2 is still 0. So we get x is 0 is one answer. And then on the other one, we subtract 4 on both sides, and we just get x is equal to negative 4. So now we have our 2 x-intercepts. Now, do you all want me to work this using the quadratic formula just to show you that you would get the same 2 answers? Or are you happy with just doing it this way?
You can show. Can you show, please?
I can show it. That's
Yeah.
fine. I can do it. I'll work it quickly over here on the side. Had we decided to use a quadratic formula, we would have needed to identify A, B, and C, which we already did earlier. A was that, B was that, and C was 0. And then we'd have to use a quadratic formula, which again, I would provide you on the tests. Okay, so that's the formula. Let's plug everything in. So negative b would be negative 8 plus or minus the square root. Then we need b squared. That's negative 8 times negative 8. That's positive 64. Minus 4 times a, which is 2, and then times c, which is 0. And then 2 times 2 on the bottom. And something interesting happens here because of this 0. Are y'all okay with the idea that everything there goes away?
Yep.
All right. And that's actually a good thing because it's going to make this much easier. We have negative 8 plus or minus the square root of 64 is still there, all over 4. And now you have to figure out what is the square root of 64. And you could use your calculator, but that's a perfect square. So that's 8 times 8. So we know the square root of 64 is 8. So no more square root symbol, right? And now you have to do the two different options with the plus and the minus. So if I do the plus, I get negative 8 plus 8 over 4. And if I do the minus, I get minus 8 minus 8, or negative 8 minus 8 over 4. So on the top one, do y'all see that that's just 0 over 4?
Mm-hmm.
And then 0 divided by anything is 0. So we get 0 as an answer. And then on the next one, we get negative 16 over 4, and that gives us negative 4. And those are the same two answers we got by factoring. Just took us a little longer. Okay, what's next?
Y-intercept.
Y-intercept, right? So step 5, we get the Y-intercept. Here we just plug 0 into the function. And if you do that, you'll notice you'll just get 0 because it just kills everything off. So now we're ready to put this all together on a picture. So I'm going to start out with my vertex. My vertex is at -2, -8. So it's down here. I have x-intercepts at 0 and -4. So on my x-axis at 0 and -4. I have a y-intercept at 0, but I've already put that point there. Okay, so that point there at the origin where the cross comes together, that's y equals 0. So that x-intercept is also a y-intercept. It's the same thing in this particular problem. Now, just your axis of symmetry. I think it's kind of easy to see this. Hopefully it is for you. You can draw a little U here. Yeah. There we go. Okay. That's pretty good, actually. All right. What do y'all think? Just follow the steps, right? Let me take a look at one here. That one looks pretty interesting. Let's do one more. Let's do this last one here. So for this one, A is what?
-1.
-1. B is
4.
4, and C is 3. Okay, this thing opens down because A is a negative number. In terms of the vertex, we have H, which will be -B over 2 times -1. So be careful there. It's the opposite of B over 2 times A, but A was -1. That's -4 over -2. That's +2. And then to get K, we plug that 2 into the original function. And again, be careful here. We're doing -1 times 2 squared plus 4 times 2 plus 3. So again, I want to just reiterate that negative in front. Treat it like a -1 and just wait. Don't do anything with it until after you've squared the H that 2 that you're plugging in. Square that first. So we'll have -1, and then 2 squared is 4, and then 4 times 2 is 8 plus 3. So we get -4 plus 8 plus 3. And I think that's 7. Yeah. So 2, 7 is my vertex. I've got a quick sketch. To the right, 2 up 7 is somewhere up there. And it opens down. And because it opens down, I can see that I have 2 x-intercepts. And that means I've got to go and do the work to find them, right? So to find the x-intercepts, I take the original function, I set it equal to 0, and now we have a quadratic equation. Now for that one, maybe you could try factoring. It's not going to work. That looks a lot like a problem we've done already, but we'll work through it. Okay, I'm going to actually go through this. So I'm going to use a quadratic formula now. All right. I'm going to use the fact that x should be equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And for us, this should be -4, that's the opposite of b. And then b squared should be 16 minus 4 times a, which was -1, and c, which was 3, all over 2 times -1. Okay, so that's just me plugging in everything, you know, a, b, and c getting plugged into the formula. Now, we talked about this last time. When you look at this piece right here in yellow, if we count the number of negatives we see, we can see we have 2 negatives. And I said if you see an even number of negatives, that means that it's going to turn into a plus. If you see an odd number of negatives, it should turn into a minus. So this should be -4 plus or minus square root 16, and then it'll be a plus, okay, because there were 2 negatives. And then you just take these numbers and multiply them. Don't worry about the signs. 4 times 1 times 3, that should give me 12. And then all of that's going to be divided by -2. I also pointed out last class that you should not try and do anything with those two, like -4 over 2. Don't try and do it. Okay, so let's not pay attention to that. Let's just keep working out the top. Running out of room here. -4 plus or minus square root. Now we can do 16 plus 12, that's 28. And then divide all that by -2. And unfortunately, the square root of 28 is not a perfect square. So this is where you break out your calculator and you do the square root of 28. And we're going to get a decimal, and we're going to round it to do 2 decimal places. 5.29. So -4 plus or minus 5.29. And again, the square root symbol is gone, right? We've already taken the square root, so don't write it again. And I'm really running out of space here. Bring this right here. So now I have 2 different scenarios. I have the plus that I have to look at, and then the minus. So if I do the plus, it'll be -4 plus 5.29, and then divide that by -2, and then -4 minus 5.29, and divide that by -2. All right, I'm going to get my calculator out. Does anybody have the top one there? The whole answer? This one here?
On that one, I got -0.65.
Yep, okay, good. So you rounded 2 decimal places, that's fine. And let's see, on the next one, $4.65. So remember, when you do this on your calculator, do everything up top first. Okay, do everything up top on your calculator and hit enter, and then put divided by -2. So do everything up top here, hit enter, and then everything divided by -2. You should get those 2 answers. Okay, we've got the X-intercepts. Let's do the Y-intercepts, or intercept. There's only one. There's always only one Y-intercept. All right, so the Y-intercept, we plug 0 into the function, which leaves us with just 3, because all the X stuff goes away. I think we're ready. Start with my vertex. I go out to the right 2 and go up 7, put a dot. That's going to be the highest point of my graph because my parabola opens down. My X-intercepts are going to be a little tough. -0.65 is not quite -1. It's kind of in the middle. So you want to kind of just eyeball this. I don't know if y'all can see my dot there. I'm going to say that's -0.65. And on the test, I want you to label these points so I know what they are. And let's see, 4.65. So here's 5. 4.65 is about right there. Am I missing anything? Anything else I need to put on this graph?
The Y-intercept.
The Y-intercept is 3. That puts here. It's 3 units up, right, on the Y-axis. Got my axis of symmetry. And now I'm going to draw this thing. And I'm going to go off to the left first, try and connect the dots here. And then to the right, I'm going to just kind of do the same thing as best I can. There we go. That's it.
I have a question.
Yep.
When you were getting the Y-intercept, why did you put 0 as a function?
Because you always got to do it by 0, right?
Doing the Y-intercept, why what?
Why did you use 0 for the function on the?
Oh, I did to get 3. Is that what you're saying?
Yeah, to get the. Yeah, I'm just not sure where that 0 came from.
For the Y-intercept, you're always plugging in 0 every single time.
Okay.
Yeah. To find the X-intercepts, you set the function equal to 0, right? To find the Y-intercept, you plug 0 into the function. So those are 2 different things. So
that makes sense.
You got it? Okay. So
that makes.
Okay. Some things to pay attention to when you take the test. Let's say that you're working through a problem, okay, and you get to the end and you put all your information down. Let's say you have a vertex right here. But let's say that your X-intercepts are here. What do you think that's telling you? Because your axis of symmetry has to go down the middle like this, right? That should be an indication that you messed something up. Because your X-intercepts should be equally spaced on the sides of that blue line. You know, here, if you try to draw this, I mean, it would be like, I don't even know what you would do there, but that doesn't look like a parabola. It looks like a parabola that's getting blown over. Parabolas have to be symmetric. So if I were you and I had this information, right, then what I would do is I'd say, okay, I need to just go double check everything. You know, was my vertex right? Maybe the vertex actually belonged over here, which would make more sense. But it could also be that you messed up a sign on the X-intercept, and maybe that X-intercept belongs right here. Okay, so just be aware of that when you go to graph. If things don't look right, there's something wrong with one of your calculations. All right, that's it. That should get you through this, you know, and that should be enough to get you through the homework. And now we're going to move on to applications, all right? And we're really only going to talk about one application of quadratics. I think in class last time I talked about how quadratics are used all over the place. But there's one in particular that, there's one application in particular that I think is extremely useful. And it's interesting to talk about, I think. So let's say that you have a building. And let's say you're standing on this building. And let's say you throw a, I don't know, a tennis ball off the building, right? It's gonna go and it's gonna fall, it's gonna hit the ground, right? So as it's traveling through the air, right? As it's traveling through the air, let me back up. As the ball starts to drop, it starts to speed up. The further it drops, the faster it gets. It gets faster and faster and faster, right? So let's say I throw the ball, and let's say after 1 second, here's where it is. 1 second. That's where it is. If I look 1 second later after that, the ball will not be here. In other words, the distance it traveled in the first second is not going to be the same as the distance it travels in the second second. It's actually going to have traveled further because it's speeding up. So now after the second, that's weird. Okay, after 2 seconds, the ball has now traveled much further than it did in the first second. Does that make sense to everyone?
Yeah.
And then at the third second, shoot, it may have even hit the ground. It may be down here. Depends on how high we were. But in that third second, it definitely traveled further than it did in the second second. So, you know, it's like as it speeds up, it gets faster, so it travels further in the same amount of time. So this type of behavior is not linear. In other words, like when you think about like how much money you make at work, if you work, like if you're hourly, like to say you're an hourly employee, you know, after 1 hour of work, you get paid, let's say $20. After 2 hours, it's $40. After 3 hours, it's 60. So it just keeps going up by 20 each time. That's linear. It's the same rate of change. But when objects are falling, the rate of change is not linear. It turns out that it's quadratic. And so, you know, this was, you know, studied quite a bit, you know, back way when humans were just trying to figure shit out, right? And we were able to figure out that every object on Earth falls the same way. So we actually have a function, a quadratic function that will tell you exactly where something will be. If you just, you know, drop it off of a bridge or a building, we can actually predict exactly where that will be. And what's even cooler, cooler thing about that is that it doesn't matter what it is. It could be a tennis ball or a bowling ball. The function works for both. So usually in a classroom, I do this as an example. I don't know, maybe I can do it in here. Let me try it. Let's see if this gets, don't know how this is gonna go. Let's see how this goes. All right, so maybe y'all can see my camera. Can y'all see me okay? Maybe I should make my camera a little bigger and stop sharing my screen. Then I think I can, what happens when I do this? When I say, does that make it big on your screen?
Yes.
Yeah.
Yes? Okay, so let me try. All right, so what I have here is a book, right? And then I have a piece of paper. Now, if I drop these at the same time, which one of these will hit the ground first?
The book.
The book. Okay, so I'm going to do, I have to turn off my fan because the fan is causing a little bit of an issue. So I'm going to start it from here. I don't know how loud this is going to be for you, but just be prepared. So I'm going to drop these at the same time. Let's see which one hits the ground. All right, so the book hit the ground first, right? So my question is, why did the book hit the ground before the paper?
Well, the paper has the air helps the paper stay up more longer, right?
Okay, so the air you think had an impact
Yeah,
on this happening? Yeah?
for the paper, yeah.
The amount of weight
Okay,
of
do you
book
think
has-
it had to do with how much these weigh?
Yeah.
No.
So,
No, because everything falls at the same speed. I mean, everything will, like if you have a brick and something lighter and you drop it, it's both gonna hit the ground at the same time.
okay, so yeah, you're bringing up a very important point, all right? And that is that, like I just said to you, we have a quadratic function that will tell you if you drop something, like how far it will have dropped, and it doesn't matter what it is, all right? But that didn't happen just now. There was a difference between these two, but it has nothing to do with the weight, all right? It has everything to do with air. So if you believe, and a lot of people do believe, that a book will drop faster than the paper because this is heavier. I'm going to prove you wrong right now. So what I'm going to do, I'm going to back up here. I'm going to take this piece of paper. Now, remember, if I drop them, obviously the paper is going to go slower. This will hit first. But if I put the piece of paper on top of the book, and I did not, it's not taped on there or anything, it's just going to rest on top of the book. If I drop these now at the same time, if you think that the book drops faster because it's heavier, then what we should see is the book should fall away from the paper because it's dropping faster than the paper and hit the ground, and then the paper will follow, right? If you think it's because of weight, but watch what happens. They just went together, okay? So it has everything to do with air and has nothing to do with how much something weighs. And that was highly debated. And there were people that, how do I unpin my video?
You look great.
Oh. Okay, cancel spotlight, there we go. Is that better? Are we back to normal now?
Yeah.
Okay, so, you know, there was huge debate about this idea for a long time, and scientists finally were like, okay, no, we're right. You know, everything on Earth drops the same. So if you drop a book and a bowling ball, they should hit about the same because the air doesn't have an impact on them as much as a piece of paper. The air actually slows the paper down more than it does the book. So if we could take air out, right? If there were no air on the Earth, well, we wouldn't be here. But if there were no air, no matter what you dropped, they would all fall together. In fact, one of the first experiments that we did when we went to the moon was, I don't know if you've ever seen this video of the guy in the spacesuit on the moon. He has a feather in one hand and he has a hammer in the other hand. And he drops the feather and the hammer on the moon and they both drop together. And that's because there's no air on the moon. And so everything should drop the same. And at that point, we already knew it was true. It was kind of like a, you know, yeah, see, you know, we told you so, here we go. Because there were a lot of people who didn't believe that was true. So if you can believe that every object on Earth drops at the same rate, if there's no air, then there should be a formula that tells you how far it's gone after a certain amount of time. And I'm about to give you the formula, all right? So I'm gonna write it down first, and then we'll talk about it, all right? We'll talk about what it all means, because when I write it down for the first time, it's gonna look really weird. So this is the function for falling objects on Earth. And I have to put in here, no air. So this formula only works if there's no air. And I know you're going to be sitting there going, well, what the hell's the use of having a formula that doesn't account for air if there's air, right? Well, look, we do have a formula that does account for the air. We do, but it's more complicated. And this is the way science and physics works. You start out with the most basic example first, the simplest example, and then you start adding in the variables that make it more complicated. So it's like when you're first studying the way objects move, you know, if you take, let's say, my calculator, and you take it and put it on my desk, and you go to drag that calculator across the desk, right? I have to apply a force to move it. When you first start studying that, you do not take into account the friction. You say, you know, there's friction between the calculator and the table. You know, if this were a rubber table, it would be harder to move it. So the first types of physics problems you ever do, you just say, forget friction. Let's just talk about, if there were no friction, let's talk about it. And then you add the friction, it becomes more complicated. Well, this is the same thing. We're talking about objects falling on Earth. We're gonna neglect the air, take it out, and see what the formula looks like. And that's all we're going to study in this class. We're not going to go anywhere beyond that. Just trust me when I say that there are more complicated formulas, and that's what makes physics difficult, right? Is trying to account for all the different things that could happen. You know, air, humidity, all sorts of different things. So here it is, ready? It is d of t. So instead of f of x, we've been dealing with f of x, right? That notation f of x. We're going to now use d of t. So this is a function. We're using d instead of f. We're using t instead of x. D of t equals -16 t squared plus v with a little 0 down here. I'll explain that in a minute. Times t plus d with a little 0 right there. Okay, now let me explain what all these things are. First of all, t is just time, and it's measured in seconds. So in this formula, t will be time, and it's measured in seconds. D of t is the height of the object at time t. I'll explain that a little more in a second. V with this little 0 below it is, we say that V naught is the starting velocity of the object. I'll explain that in a minute. Let me just write this all down. Positive if up, negative if down. Again, I'll explain that in a second. And then D naught is your starting height. And this is measured in feet. I should also say up here, the object, the position after a certain amount of time is also measured in feet. Okay, so I want you to look at that and see how similar it is to this. Okay, so for the one in green, the variable here is x. For us, the variable is t, right? We have t squared, t, right? That's like the x squared, x. So for us in this, on the formula for a falling object on Earth, what's a?
The 16, -16?
-16 is the a, right? Now, what's the b?
The V.
The b for us is the v naught, isn't it? And that's not a number that's given to us, okay? That v naught is the starting velocity, okay? And what we mean by that is this. Let's say I have two objects that I'm gonna drop, okay? Let's say these were the same thing, like they're both exactly the same pins. If I just drop them from the same height, if I just drop them, they're gonna hit exactly the same. Exact same time they'll hit. But what if I were to take this one here, this pen, and I were to actually throw it down, like actually throw it out of my hand downward, then it should get to the ground before this one does, right? But if I take this one and throw it up first, then it's gonna go up and then back down. And so this one right here will get there later than this one. So this formula accounts for, well, the formula can account for any initial velocity that you want to give the object. If you want to throw it up into the air or you want to throw it down, that will take care of it. You can think about it like a bottle rocket or something. If you shoot it into the air, that you're giving it an initial speed, okay? So the V naught takes care of that. And then the D naught, I'm running out of colors, the D naught is just our C. And that's the starting height. So if you're on a building that's 100 feet tall, D naught would be 100. All right? Any questions on this? I'm going to work through an example, but I just want to make sure y'all can see the similarity in terms of that this is a quadratic function. Since it's a quadratic function, we should be able to graph it, and we should be able to determine everything about it, right? The highest point, the X-intercepts, all those things we should be able to figure out. So let me do an example, all right? And I'm going to refer back to this. I feel like I'm forgetting something. Starting height. Oh, okay. Yeah, there's one more thing I wanted to talk about. This A that we have here. Okay, the A here is -16. And notice that that's the only number that we actually know for sure. As long as we're talking about an object falling on Earth, that's -16 every single time. Does anyone have a guess as to what dictates that that's -16? Like, what is it that makes it -16?
Gravity.
Gravity, exactly. It comes from the idea of the gravity of Earth. If we were on the moon, this number would change. If we're on a different planet that had a different mass, then the number in front would change. But that's all that would change. If you're talking about any planet with any mass, and you drop an object on that planet and let it go and start falling, I guarantee you there's a quadratic function that would model what's happening. The one thing I wouldn't be able to tell you right away is what that number out front is, -16. Now we can figure it out. It's actually not that hard to do. But for Earth, it's -16, but for other planets, it would be something else. So, okay, I think we're ready for an example. And I think I'm going to try and type this in. A rock is thrown upward with a speed of 20 feet per second from a 30-foot bridge. Okay, so that's the physical problem being given to you. You've got this bridge. Whoa, no you don't. You have this bridge. You've got this person standing here on this bridge. They're going to throw a rock upward, okay? They're going to throw a rock up. It's going to come down and hit the ground down here, all right? When they throw it into the air, we know that it leaves their hand traveling at 20 feet per second. But as soon as it comes out of their hand, gravity takes over, right? So, and we also know that the height of the bridge is 30 feet. So the height of this bridge is 30 feet off the ground. Is that a pretty good, can you see that in your mind, what's going on?
Mm-hmm.
Okay, so here are the questions. First question, part A. Find the quadratic, can't type, function which gives the height of this ball as a function of time. In seconds, the height we want in feet. Okay, so the first thing we want to do is come up with a mathematical model that's going to tell us where this thing is going to be. And I should say here, we're taking air out, okay? We're taking air out of the equation here. So that means we'll be able to use that formula. All right, that's the first part. Okay, the next part is what is the maximum height of this ball. Oh, wait, it's a ball. It's a rock. Sorry. It's not a rock. It's not a ball. It's a rock. Let me change that. Rock. What is the maximum height of this rock? All right, the next thing is when does it reach its maximum height? Next question, when is the ball 10 feet off the ground?
Rock.
Sorry, is that a question?
A rock.
Ah! I guess I want to throw a ball instead of a rock. Okay, when is the rock 10 feet off the ground? And then finally, when does the rock hit the ground? All right, there we go. All right, there we go. Okay, let's do this. Part A. Okay, so part A, we know this is an object that's going to be falling on Earth. It's under the influence of gravity only. So we know that the formula must look like d of t equals negative 16t squared because we're on Earth, plus some number in front of t plus some other number d naught. So do we know v naught and d naught? Is it given to us in this problem? So remember what they were, right? What was d naught?
Starting height.
Starting height. Are we given the starting height of the ball?
30 feet.
Yeah, we're gonna ignore the height of the person, okay? And like where it left their hand. We're just gonna say it was 30 feet when it left his hand or her hand, okay? So we do know that 30 feet should be our d naught. And do we know v naught, which would be the speed of the rock when it left the person's hand, which should be
20 feet per
20
second.
feet per second. That should be v naught. Now, the big question is it going to be plus 20 or is it going to be minus 20?
Minus.
So when you go up here, look at what I wrote up here in green. The starting velocity of the object, it'll be plus if it's thrown upward.
Oh, yeah,
It'll
yeah,
be
yeah.
minus if it's thrown downward.
Yeah,
Okay.
throw upward.
So in this case, it's thrown up, so we're going to use a plus 20. Had this person thrown the rock down off the bridge, then we would use negative 20. All right. Okay, so I think that should be enough for us to come up with the function. D of t equals negative 16 t squared plus 20t plus 30. And there it is. For this particular rock on this particular bridge, that will give you where it is at every point in time. So think about it this way. This is a parabola. Do you all agree? That is a parabola?
Yes.
Okay. And it opens which way?
Down.
Down. Okay, so this is what I can tell you so far. It opens down. Can you tell me what the y-intercept is?
30.
30. And wouldn't that happen if you plugged in 0? So think of t as time. If you plug 0 into this, right? I'm getting a little ahead of ourselves, but if we plug 0 into this, we get 30. That means at time 0, where's the rock? 30 feet high, right? That's, well, that it's about to leave the person's hand, right? Right when the clock's about to start, it should be 30 feet high. And then the ball's going to go up. And then it's going to come back down and it's going to hit the ground, right? That's what's going to happen. So look at part B. What is part B asking for? What is the maximum height of the ball? What are they looking for?
When you throw it up, right?
Yep, when you throw it up. But look, in terms of our picture of our parabola, what would the maximum height really be referring to here?
Where it starts,
The what?
where it starts at the 30 feet? Or would it be that vertex?
Wouldn't it be the highest point? Wouldn't it be right there in black? Wouldn't that correspond to the highest point of the rock?
Yeah.
Yeah.
Okay, but what is that to us? Like in the problems we were doing before this, what was that?
Vortex?
That's the vertex, yes. But more importantly, it's not the whole vertex. It's only one of the two pieces.
Oh, the Y.
Which piece is it?
The Y-intercept.
Yeah, it's this right here, right? That's what we want to know. And remember, that is a point. It's H, K. Which of those two, H or K, would represent the height?
Okay.
The K. So when you look at it this way, part A is asking for us just to come up with the function. Part B is really asking us to find out what K is from the vertex, isn't it?
Mm-hmm.
And what is part C doing? It's saying, when does it reach its maximum height? When, time, when. Well, time is the T. And T is like the X has been for us. So wouldn't that correspond to this down here? Which is actually the H of the vertex. Do you all see that? It's an important connection to make. The K gives you the actual height, the maximum height, and then the H gives you when it happened. What about, let's skip D, let's go to E. When does the rock hit the ground? What is that asking for?
The time?
Mm-hmm. It's the time, but in our picture, what is it?
The X. The X.
Yep, it's the X-intercept, right? This right here, this point right here, which we normally refer to as the X-intercept, right, is when it would hit the ground. So this really wants the X-intercepts. Now let's do D, because D, you know what, let's take D out. This class, we don't need to do D. We won't do that. We'll just scrap it. That's all I'll ask you on a test. Those 4 things there. Okay, so the big idea is this. You have a word problem. As long as you can convert that word problem into a function, a quadratic function, then I'm not asking you to do anything different than what I was asking when I asked you to graph it. You will have to find the vertex and the X-intercepts. That's it, right? That's all you have to do. You just have to know which answer goes with which. So if you want to know the maximum height, you're looking for K. If you want to know when it reaches its maximum height, you're looking for H. And if you want to know when it hits the ground, you're looking for the X-intercepts. So let's just crank it out. Let's go get the vertex. Now, when we get the vertex, we have to start with H, don't we? Even though the question is asking for K first, we actually need H. We can only get H. We have to get H before we can get K. So what will H be for us? The formula is negative B over 2A. So for us, what's negative B?
Oh, the 20?
Negative 20 over 2 times A. What's A?
16.
16.
Negative 16.
Right? So we're going to negative 20 over negative 32. And this is the first time that we've actually had an ugly number. .625 is what I'm getting. Now I'm going to use 0.625 because it doesn't keep going. It stops 0.625. So I'm going to try and be as accurate as I possibly can. That's H. Let's find K. So how do we find K? We take the answer and we plug it into the function, don't we? So we plug into the function d 0.625, which means we're going to take negative 16 times 0.625 squared plus 20 times 0.625 plus 30. Now you'll need your calculator. You're going to have to square this first. So negative 16. I'm gonna have to round now. I'm gonna go 0.39 plus let's do that 20 times 0.625. Are there any questions while I'm writing this down? Okay, I'm going to do the negative 16 times the 0.39, which is negative 6.24 plus 12.5 plus 30. I'm just going to do all that on my calculator now. $36.26. Let's see if we can't answer parts B and C, because don't we have H and K?
Yeah.
Okay, so let's answer B. What is the maximum height of this rock?
36.26 feet.
It's 36.26 feet. 36.26 feet. That's it. So the ball really only went up how much? How many feet did it go up? From where the person threw it? It only went 6.6 feet up, and then it started coming back down, right? Now, part C says, when did it reach its maximum height? So that's a question of how much time did it take after it left the person's hand? How much time did it take to reach that peak? And what's our answer?
The 0.625
0.625 what?
seconds.
Seconds. So just a little over half a second is how long it was going up for. And then it reached the peak, and then now it starts dropping. So we want to know when it hits the ground now, right? So we need the X-intercepts. So what that means for part E is that we have to take the quadratic and do what with it?
Put 0.
Set it to 0. And yeah, this is going to kind of suck, but we have to use quadratic formula. I'm going to write the quadratic formula down, but I want you to notice I'm using t instead of x because our variable in here is t. So I'm putting t equals negative b plus or minus the square root b squared minus 4 times a times c all over 2a. So I'm going to just give you the answer here. I'm not going to plug any of that in. Okay. Well, you know, I'll plug it in, but then I won't. I'll compute it in a minute. So negative b is negative 20 plus or minus the square root. Okay, b squared should be 20 times 20, that's 400, minus 4 times negative 16 times 30, all over 2 times negative 16. Negative 20 plus or minus square root of 400. It's going to be a plus because I see 2 negatives there, right? There's 2 negatives there, so it's an even, so it's going to be a plus. And when you put those together, you get 1920 all over negative 32. Now I'm going to keep going here. This is negative 20 plus or minus square root. Okay, what is that? 1920 do. I need to do on my calculator the square root of 23, which gives me 48.17 over negative 32. And now I have to do both the plus and I have to do the minus. Are y'all following what I'm doing here?
Yeah.
Okay. I know I'm moving kind of quick through it, but I'm trusting that you could work on your calculator, eventually get this. I get two answers.
So you got to do the negative 20 plus 48.17 and then divided by negative 32. And then you got to do the minus.
And then do divided by negative 32. So I have two answers. Do these answers both make sense or no?
Not really.
Remember, the question is, when did the rock hit the ground? When did the rock hit the ground? And I'm saying at negative 0.88 and 2.13.
Only the positive would make sense, right?
Only the positive makes sense. The reason why we're going to scrap the negative and just use our answer here of 2.13 seconds is because mathematically, if you look at the picture of this parabola, right, like the parabola actually extends backwards too. And there is a second x-intercept here, which we found at negative 0.88. But the thing is, the parabola, even though mathematically we have a parabola, we're only considering a certain part of the parabola because it applies to a real world problem. So we don't have a negative time. We only have time starting at 0 and going positive. So even though we get two answers, we're only going to consider the positive answer. Does that make sense?
Yeah.
Yeah, so we will only need to figure out the positive answer then?
Yep. Yep.
Okay.
Okay, so let's just kind of summarize this whole problem. Person standing on a 30-foot bridge, they throw a rock into the air, give it a speed of 20 feet per second, leaves their hand, it travels up. It takes 0.625 seconds for it to reach its peak. When it gets to its peak, it's 36.26 feet high. And then now it starts to drop to the ground, and it takes a total from when it left the person's hand, it takes a total of 2.13 seconds for that rock to get back to the ground, not to the bridge, but below the bridge onto the ground. And that is if you are talking about an object, a rock being thrown on Earth, and you're taking out air. Which, if you really did this experiment, it would be really close to 2.13 because rocks are not impacted by air very much. I'm talking about a rock the size of a ball, like a golf ball or tennis ball. Any questions?
So,
Can you go back to that first page?
Go up. This part?
No, the first page where you like kind of laid everything out.
What do you mean? Like
The page right before that right there. That right there.
Oh, this right here. Yeah.
So how do you know? Because you can either use this equation or you can use the factoring equation too, or no?
For what? For the part when we found the x-intercepts?
Yeah.
This part right here?
Yeah, that part.
You could have tried to do the factoring. It's just the numbers are kind of big there.
Oh, okay.
And most of the time on word problems like this, most of the time your answers are going to be ugly decimals because the real world does not care about giving you pretty numbers.
Mm-hmm.
And most real world problems are going to be something that you can't factor. I would have to especially really pay attention to how I'm making the problem. if I wanted it to factor for you.
Oh, okay.
So somewhere on the test, you will have to use a quadratic formula. There will be no way around it. You won't be able to factor it. And this would be a good example of that.
But either way, you're going to get the same answer, right?
Oh, yeah.
Yeah.
If you can factor it. And
Yeah,
you can't always factor it, though.
Yeah.
Yeah. So normally in like a normal college algebra class, I like to talk about something at this juncture. I just don't know if I should. Because, I don't know, everyone's just so sensitive nowadays. You know? So I think what I'm going to do is I think I'm going to talk about it, but I think I'm going to not record it. And that way I'll feel a little bit better about it, but it's not recorded. I don't think what I'm going to say is bad in any way, and I don't mean it is coming across that way. But like I said, it's 2020 and you just about can't say anything.
True.
Okay. So I will record later after we're going to take a break.